evening, and welcome to another episode of Data Structures and Algorithms with Open Delta. Today's this video, as you can see on the screen, is titled Why Algorithms Matter, and we'll be going into the importance of algorithms. Previous video developing, we went over the importance of data structures, right, and why choosing the right one, how it can affect the performance of your application, right? And we spoke about two data structures, being the array and the set, and we delved into the various operations, four major operations that can be performed on these two data structures. We also performed some analysis on them to see the number of steps required for those operations for each of the sets, right? So today we're going to introduce the concept of an algorithm, say what it is, from just the colloquial term, and then how it's applied or referred to in computer science. And then from then on, we'll go into the importance of choosing the right algorithm, when to choose the right algorithm. And then finally, we'll analyze the performance of another data structure, which is the ordered array. So it's going to be algorithms, and we're going to get introduced to the ordered array. So let's jump in. So what is an algorithm, essentially, right? So an algorithm, you can think of it as a step or a particular process that you take to accomplish a goal. Or as you can see on the screen, it's an algorithm. An algorithm is essentially a process for solving a problem, right? And then on the right-hand side, you can see that I have prepared an algorithm for making one of my favorite meals, which is rice, right? So you know how we normal when I want to make some rice, I'm going to start off by grabbing a pot. I'll pour the rice into the pot. Then from there, rinse the rice. And then, okay, well, I think I've jumped. Submerge the rice in the pot with water, and then place the pot on the heat source and cook till ready. And as you can see, I am ready, right? So major operations that you perform with an algorithm, as we mentioned before, reading, searching, insertion, and deletion. And there, for a specific operation, there's like multiple or different types of algorithms that you can use to achieve a specific purpose, right? So the importance of this, why we're here right now, is just to discuss how we go about selecting which one is the best one for the specific operation. Right, so the ordered array, like in the previous episode or in the previous video, we spoke about the standard array. I introduced what an array is, right? If you don't remember, check out the description below, or you can see the hyperlink there. So what is an ordered array, right? As the name suggests, all the values in the array, right, are ordered from either increasing to increasing from the least to the most, right? So in increasing order, right? Standard array, like, so a difference between standard arrays and ordered arrays, right? You can essentially just add a value in the array without considering the order, right? As you can see, like on the right-hand side there, you can see that we want to insert 83 into this array. We can just add it there, right? Number of operations that it will take, 1, right? Because we added it to the end, right? However, for an ordered array, right, you see that we can't just add 83 at the end, because then it breaks the order. It breaks the order of the array, right? So we have to look for the correct position, and that's the correct position, right, at index 3. So let's say, okay, so this is going to be like the particular steps that we want to take to insert the value at 83 to this array. So step 1, I have to check the value at index 0, right? And I have to do this quick check. If the value at this index 0 is greater than 83, then we know that we have to insert 83 to the left of that value. Else, then it's to the right, right? Then we continue doing this, right? Continue doing that. And then you see, so we get to 17. Let me just go back so that we get to 17, right? 17 is less than 83. So therefore it's not going to be on the left, it's going to be on the right. So we have to move to the right. Then we get to 75, right? 75 is less than 83, right? So it has to be on the right and not the left. So we move then. And we see it's 186 is greater than 83. Therefore, this value would have to go to the right of 186, right? And that's, so we make space for it. So we do that by moving 186 to the right, and then we can now add the value. Okay, so that's the insertion operation, right? As you can see, that it requires a search before we can actually insert, and that's the reason why we do that, or why that's necessary, is because we have to keep the order the well, the order of the array, right? And that's the key difference between a standard array and an ordered array. And for the insertion operation, because we have to do a search before we can insert, the standard array is more efficient than the ordered array for insertion, right? However, the standard array, or the ordered array rather, has a super power for the insertion operations, right? It should not be, in fact, that should be the search operation. Superpower for the search operation. And so let's go back to our previous video. We spoke about how the search operation works. And essentially what we discussed in that video was the linear search, right? And so, we're just checking each value of the array until we find the value that we're looking for, or if it's not there or not, right? So how does this differ when it comes to a standard array and an ordered array? We'll see now. Right, so we're going to search for the value for 33 of 33, and we're going to start at index 0. We're going to say, okay, index 0, is this 33? No, move to the left, move to the right, sorry. And then is this 33? No, move to the right, move to the right, And as you can see on the screen, it says 33 is not there. So unfortunately, yeah, we didn't get the value there. And the number of operations took was n, and where n is signifies the number of elements in this array, right? So this is the worst case scenario for searching a standard array. Okay, but now let's look for an ordered array, right? We also have to do, okay, let's see the superpower, right? So I start at index 0, which is 5. It's not that. I go at 17, right? That's not that. I go at 75 and say, hey, hold up. This is 75, right? So this is an ordered array. Like if we skipped like up to the 75, we skip 33, then there's no point in continuing any further, right? Therefore, let's just stop, right? And that's why that emoji did stop right now. And the number of iteration that took was 3, instead of us having to go through the entire array to decide, oh, it's not there. Okay, now this is essentially the process flow or algorithm for linear search and ordered linear search for standard array and ordered array, right? You can go through it. I'll pause, but I'll just move right along. And then we're going to jump into a code break. Great, let me show you. Okay, so now we've gone to our code break. We're gonna jump into some code, right? That's why it's called a code break. So now we're gonna code this algorithm, right, into Python. As you can see, this is a Python script, and essentially what happens is this is called a linear search. Our parameters are an ordered array and a search value that we're looking for, right? So we have our search index. We initialize it at 0, right? Okay, or let me just go through okay, we start, right? We read a value at memory location, and then we check if is this value greater than the value of interest? Yes, then we know we can stop. If it's not, is this value the value of interest? If it is, then we can store the index and we can stop, right? If is this value of interest? No, then we have to check, is this the last index? Right? If it is, then it's not inside there, right? Then we stop. No, we move to the next index. Essentially, that is what this piece of code is doing, right? So we have our ordered array. We're going to enumerate through that. And what that means, essentially, we're going to split it up or unpack it rather into its index and the value at that index, right? All right. And then we're going to check, is this value, we're doing that right over here? If it is, then, we're going to break out to say it's not in here, right? And then we have our elif. If the value is the value of interest, then we also break out, right? And then after that, we check like if our search index is not equals to 1, right? So if it's not true, right, we return 0, else we return the search index. Okay. Yeah. So we run that, and then we can also run that. That should be running, but it's taking a bit of time, so I'll just pause. As you can see, 14 is not in this index, is not here. So therefore, yeah, that's why we say it's a 0. So it's false. We didn't find it. So if you look at 3, what we should have is 0. Great. Search array is in 3 is in array at index 0. So we know where it is, right? So that's essentially how that works. So we can jump back and let's continue explaining what ordered arrays and algorithms are they important. Okay, so we've gone through this. So now we've gone through that. Now, why algorithms matter, right? So we're going into now the algorithms. Now, essentially, what we've been doing so far has been the linear search, right? However, there's another way of doing this operation of looking for a value, and essentially there's another algorithm, and that algorithm is called the binary search. And the binary search essentially is a superpower of the ordered array, right? So, have you ever played the guess number game, right? Essentially, how the game works. You're given a range of possible values, for example, 1 to 100. And essentially, you as a player, you have to take a guess. And then if you take a guess, I'll tell you higher or lower. And then you repeat this process until you get the right number, right? So on the left, our computer is asking us to guess a number between 1 and 10, right? So let's guess. Okay, I'm going to guess 5 because I want to be clever and just to say, and you would see why that's a bit of a clever move there. When we get to 5, when I say 5, I'll see the computer says, oh, okay, no, that's not the right number that it was thinking about. So as you can see now, everything below 5, from 5 below has been eliminated because the computer told us that 5 was the wrong guess and we should go higher, right? So 1, 2, 3, 4, 5 cannot be in our possible truth values, right? Or yeah. So I guess again, I say 8 and it tells me lower. Therefore, I know that 8, 9, 10 are no longer there. I get rid of them. And I keep on going. I say 6, this is higher. And I know like, okay, great. It's 7. Essentially, so that whole process that we've just done right now, correct, right, great, is the is the binary search algorithm, right? So then, so when you compare the binary search algorithm with linear search, right? What essentially happens is, so binary search, right? When it comes to val or arrays that are of small size or smaller size, there's no performance difference essentially. But as you can see on this graph on the right, as you can see that as the size of the array starts to increase, there is a considerable difference, significant difference, right? And the number of operations that we have to essentially perform when we're using linear search compared to binary search, right? So that's the superpower of binary search when it comes to ordered arrays. For linear search, right? So I'm just speaking about the algorithm, how it works. If value of interest is in the final index or greater than, that's essentially the worst case scenario. Then you'd have like number of steps is n. However, for binary search, every guess eliminates half of the search space, right? As we've seen before. So yeah, that's essentially it for this short little video on ordered arrays, why algorithms matter, right? We'll also now jump into a code break for showing you how to implement binary search on Python, right? So in conclusion, right, remember, there are many ways to accomplish a goal, right? There's no perfect way, right? And essentially, there's no algorithm that fits every single thing, right? That's perfect for every single situation. You have to be able to choose, know when to choose. Like right now, we spoke about the ordered array, So the ordered array, like we spoke about, is less efficient when it comes to insertion, but more super important, super efficient when it comes to insertion, when it comes to searching, when we're using the binary search, right? So if you have a scenario where you're going to be searching your data quite a lot, that's a scenario where that's a possible choice. So I'm going to use binary search to search my data. All right. Like I've said, you can look on this graph, the number of operations, right? So the choice of the algorithm that you choose will affect the speed of your code, right? So join us rather in this code break of implementing binary search with Python. Great. Cheers.
Okay, so now this is our binary search algorithm written in um, Python, right? So I'll just tell you how it goes, right? So, here's just the print. We have our input, which is an ordered array. Then we set our lower bound, right? We set our lower bound. Then we also set our upper bound, okay? And then we print this out just for readability sake, or legibility. And then we start with the number of checks that we have to do, right? So I just put it at 1. From then onwards, I say that while our lower bound is less than or equals to the upper bound, continue with this algorithm, right? So what we're going to do, we're going to calculate the midpoint of the array. We print the midpoint index, we read the midpoint value, and then we print that to our screen, right? So what we're going to now do is we're going to check if the search value is the midpoint, right? If the search value is the same as the midpoint value, then we know that we found our value, and then we can return 1. Otherwise, we can search and see that, okay, is the search value less than the midpoint value? If it is, we update our upper bound, all right? And then we proceed, okay? And then we also have to check, like, so that would exit this loop, right? But then if this doesn't come true, or this is not true, then we also check, is the search value greater than the midpoint value? Right, from then onwards, we say that the lower bound is equals to this. We update that, and then just include that. And then we increase the number of checks every time we exit this if conditions. Right. And if we don't find this, if we go through all of this and we get to a point where this while loop is no longer true, then we would now, print the number of checks and print that we did not find the value and return 0. Right. So that's how that works. We can just execute it. Okay. Once we've executed it, um, we are now running. Great. So we have this um, array from 1 to 10, and then we're looking for the index 1, right? So we can do this, and there we go, right? Took 3 checks. Now let's do a test for 100, right? What we're going to look for is the value 100. Then we can run and see how many number of, took only 7 checks for searching a space of an ordered array of 100 values, right? In the linear case, that would be like you'd have to check each 100 of the values in that in a linear search. However, with binary search, you just took a 7 checks, right? So I'll show you a spreadsheet how that looks like. So this is a spreadsheet that compares the operation of linear search and binary search, and we're looking at it as a function of data elements, right? Um, as you can see, for one element, it says 0, but okay, it will only take us 1 in the linear search, right? But if we look at the for 2 elements, it would take 1 search to find that, right? But what is interesting, like let's look at this, right? Scenario, let's say 10 elements. We'd have to search all 10. If let's say for the worst case, we're looking for 10 or the last value in this array, we would have to go through 10 search operations. However, with the binary search, it will take us 3. And then if we were to increase this to 20, right, it would only, we doubled the number of data elements, right, from 10 to 20. However, the search operation only increased by 1, right? And you can see that pattern continues. Let's go to 40 elements, 5, 80, 6, right? So you can see how efficient this search algorithm is compared to the linear search algorithm. Yeah, great. So yeah, so this is why algorithms matter when you are designing a piece of software. It's very good to know which algorithm to choose to improve the performance of your software. Great.